back. We are starting video 3 for the rotational kinematics unit notes. So in this unit, what we want to begin talking about will be something called radial acceleration. Now, particles, when they're going through a uniform circular motion, now pay attention to this uniform circular motion. This means that the angular speed is constant. So our omega, it's kind of like constant velocity. It's not accelerating. It's not changing. Now, if we do that, then the magnitude of the velocity vector will be constant. So what do I mean by that is if I have a particle, let's say it's on the circle here, and it's traveling, we'll go with clockwise, at an angular speed of omega. There will be a tangential or a linear velocity. I'll call this v naught. And I'll go ahead and put in a little bit of a radius here. So as this turns, if we have a constant angular velocity, then the magnitude of v naught and v will be the same. So what that means is that their strength or their size will stay the same. So I try to draw those vectors at the same length. But we do need to remember that acceleration equals a changing velocity over time, and that velocity and acceleration are vectors. What that means is that since velocity is a vector, it has both magnitude and direction. So even though the magnitudes of these vectors are the same, you can clearly see that the direction is not. The direction is changing. So what that means is that we have a changing velocity and we have an acceleration. So think about that for a moment. We have an acceleration without actually getting faster or slower. And to me, that just kind of blows my mind. It's kind of cool to think about. So we have something that is accelerating without getting faster. Now, we do need to worry about the direction of this acceleration. If I were to draw this out, delta v, this vector, it would equal the final velocity vector minus the initial velocity vector. And if I were to take these two vectors and put them, or just looking at them, I want to get this plus. So notice that the final velocity vector then would equal the delta v plus v naught. And whenever we add two vectors, we want to make sure that we put them head to tail. So this initial velocity vector, I believe it looks like that. The final velocity vector then would start at the tail of this one. And there we have our delta v. And notice how I put the initial velocity in the delta v at head to tail. So if I were to, it might not be too obvious here, but if I were to start drawing all of the tangential velocities that there are, and as you might imagine, there's an infinite number of them because there's an infinite number of points, collectively, all of these give me an acceleration towards the center. We call this acceleration radial acceleration. Now, a synonym for radial would be centripetal. Centripetal means towards the center. So if I had an object that's going through circular motion, we would have a tangential or linear velocity and a center-seeking radial acceleration. And we want to be able to calculate this. The formula we use to calculate centripetal or radial acceleration is v squared divided by r. Now, I'm not going to show you how to derivate this, but if you take this topic onto YouTube, there are several videos on YouTube which show how to derive the equation v squared over r. So I'll leave that up to you to go ahead and research that on your own. Now, as you might remember, we do have a bridge. This is our bridge between rotational and linear motion. And when we apply that bridge to our formula here, we see that radial acceleration also equals r times omega squared. So take a moment, pause the video if you need to, and work out the algebra to see how I went from this formula to that formula. Okay, now before we move on to the next topic, I want to talk with you guys about gravity and what it means to have weight. And if we were to weigh ourselves, we would stand on a scale. And what that does is it applies a force, a downward force, on the scale, which is our weight. The scale reacts to that by providing an equally strong force upwards, which is the normal force. So what that means is that when you read a number on the scale, you are not actually measuring how much you weigh. What you're actually doing is you're measuring what is the normal force of the scale pushing back up against you. Now, I would argue that you cannot feel your own weight. The only thing you can feel is the normal force from the ground pushing up against you. As a proof for this, imagine if you were in free fall. If you were in free fall, you would not be able to feel your weight. You would feel weightless. Even though you're still trapped by Earth's gravitational field, you're still falling towards the center of the Earth, you would not be able to feel that weight. You would only be able to feel the normal force. You would only be able to feel your weight if you had the ground pushing up against you or the normal force. The way we interpret weight is that it's our muscles fighting against the pull due to gravity. So our legs are pushing up against the Earth. That is the normal force. So how we can put this back into, bring this all back into radial acceleration. Imagine if we were to look at a spaceship or a space station. In space, we would consider ourselves to be weightless. But imagine for a second if we had a circular space station that was rotating. If you were an object inside the space station, and the space station is rotating at some sort of angular velocity or even at an angular frequency, well, your body would wish to follow a straight line path. Your body would wish to follow some path that is tangent, kind of like the velocity. However, the walls of this space station prevent you from following a straight line path. These walls provide a normal force. That normal force is preventing you from following a straight line path. So what we can do is if we are spinning in the space station, if we're spinning at the right angular speed, what we can do is we can simulate gravity. And here's how we can do that. We can do that using Newton's second law. Now remember that with Newton's second law, the sum of forces acting on an object equals mass times acceleration. But for our space station uh, problem, for the person standing in the space station, if you think about it, there is only one force acting on them. It's this force that is maintaining circular motion. So what we can say is that this force then would equal mass times radial acceleration. So looking at this then, this normal force would equal mr omega squared. And if you could get the normal force to equal how much you would weigh on Earth, well, I mean, just think about this. There are two things that affect this. I mean, our mass doesn't change. However, we can change the radius of the space station, and we can change the angular speed of the space station. So adjusting those two numbers, we should be able to find out a magic sweet spot where the normal force equals how much we weigh, and then we can have artificial gravity that way. There's a lot of barriers to this, but I would encourage you to try to work out the math for yourself to see if you can find out, what radius and what angular speed would you need for the normal force to equal how much you weigh. Now, this force rate, if we call this a radial force, because it goes with the radial acceleration. We call this also the centripetal force, not to be confused with centrifugal. Centrifugal is different. The British call it centrifugal, and it means an outward seeking force. Those forces are not real. Only centripetal forces are, center-seeking. Objects wish to maintain a straight line path because of inertia. Circular motion is unnatural. So there must be an outside force present that forces the object into circular motion. So for the space station, that outside force was the normal force due to the walls of the space station. Without that outside force, no object could make a circular turn. So another example is if we had a car traveling along a curved road. This car wishes to follow a straight line path. However, there is a radial force that is forcing the car into the circular motion. And what's providing this radial force is static friction, not kinetic. It seems like it should be kinetic since the car is moving, but friction opposes sliding, and the wheels wish to slide right around there, about that direction right there. So since the wheels are not sliding, we would consider this a static friction. Let's say we have an amusement park ride. And you guys have probably seen these before. It's spinning, we got people, and as it spins, the floor drops out and the people are pushed and stuck to the wall. If I were to take a look at the person that is stuck to this wall, if I were to look at the forces, I would see that the radial force this time is being provided by a normal force, just like our space station example. And then, gravity's trying to pull them down. Static friction is keeping them from sliding down. And we can do a whole host of problems like that way as well. All right, this concludes video 3.